Hi, this is a second lecture for the Unit 5 overview. In this lecture I'll be going over electromagnetism. Depending on how well time's going, I may also cover capacitors too, but we'll have to wait and see. So today I'll be covering electric fields, magnetic fields and induction. So let's get started by looking at electric fields. Electric fields are regions in space that exert a force on electric charges, and they arise due to objects that have charge themselves. So objects of charge create an electric field in the space around them. The definition of electric field is the force per unit positive charge placed at that point. So you have the electric field. If you were to put a unit positive charge in there, what force would it experience? So we're dividing that force by the unit charge. The equation then is E is equal to, so E being the electric field strength is F over Q, Q indicating the charge that you put in there, and the units are newtons per coulomb. So that's the definition, and it's important that that's not confused with another equation that we'll see for electric field strength later on. In fact, there will be two more equations, so this one is the one that defines it. When we are dealing with electric fields, we'll often represent that with a diagram. So in the diagram you have field lines, and there are rules for how we draw those field lines. Firstly, field lines leave and meet surfaces at 90 degrees. Secondly, they need an arrow, and the arrow indicates the direction that a positive charge would move, so they're positive to negative. And then thirdly, the more lines you have per unit area on your diagram means you have a stronger field. So stronger field, more field lines. So here's my positively charged surface, and these are the field lines coming off indicating the electric field that this charged object has created in the space around it. They're leaving the surface at 90 degrees. Because it's positively charged, they're pointing away from this, because if I put another positive charge here, it wants to move this way, not towards it, because they repel. And you can actually see as well that they're actually diverging slightly because of the curved nature of the surface, and then that means we have a slightly stronger field closer to the surface than further away. And if I had drawn more lines, then that would be clearer still. Oh yeah, more lines, there we go. So you can see this is a stronger field if I had increased the charge on here, and that helps you see the divergence a little bit more clearly. Let's have a look at some example field patterns for various types of charged surfaces. Now, here we have two opposite charges. We've got a negative and a positive charge here, and so if we draw the field around these, they're leaving and meeting the surfaces at 90 degrees, so these ones are coming into the surface, because if I put a positive charge here, it's attracted, wants to go that way. Repelling here, so they move away from there. And these field lines will interact with each other, the field lines from each object, giving us a net field. So if I put a positive charge here, it's repelled from this one but attracted to this one, so it's going to follow this curved path here. So normally these field lines will all be spreading out here, but because of the fact that there's this negative here, they're going to curve around to meet. So that's what a field pattern would look like if you had opposite charges. If we have like charges, so we've got two negatives here, then all the field lines are going into the surfaces, there's none coming out, but these ones aren't going to meet, because if I put a positive charge here, it's attracted to both of these. Now if it's closer to this charge, it's going to ultimately move towards that charge rather than this one, because they're equally sized charges. So if I put one slightly to the right, it will move over here. So, but this one still exerts an influence when it just prevents it going straight to that charge. So the net field is like that. And if we had more field lines in here, just to indicate what would happen, you'd get this pattern going, getting closer and closer, the field lines. And then here, in this region here, if you put a positive charge here, because these two charges are equal in magnitude, there'd be no net attraction one way or the other, so the charge will stay there, the field strength would be 0. Okay, if we take two plates now that are at 90 degrees to each other, so we've got a positive and a negative plate, then the field lines need to leave and meet the surfaces at 90 degrees again. So they do so, and then they gradually curve around. So from the positive plate, they gradually curve around towards the negative plate. They don't go diagonally across, okay, because there has to be that smooth change in direction due to the influence of the negative plate there. And then if we take a more interesting array of shapes, we have this shape here, I suppose like a house, that's negatively charged, and a positively charged plate there. And again we see that they're leaving and meeting the surface is 90 degrees, and there's a smooth change in direction in between them. Okay, so those are some example field patterns. Now let's look at uniform electric fields, very useful. If you take parallel charged plates, oppositely charged plates, and put, so you've got oppositely charged plates, they're parallel, in the space in between them you get a uniform electric field. You can also have a charged plate and one that is earthed as well. That's another possibility. So that's actually what I've used for this diagram. This is a positively charged plate, and that's earthed. Now, earthed means that it's 0 volts. That's why I wanted to include it, just so we're clear on what an earthed plate is, and that's the symbol for a plate that is earthed, or an object that is earthed. Now, the field lines are parallel and they are evenly spaced. So they're meeting all the requirements for the rules that we've seen so far. So they're leaving and meeting the surfaces at 90 degrees. Because this is more positive than this one, so the field lines go towards the earth like that. And the electric field strength for these two plates is the voltage difference over the distance between them. Now the units here are volts per metre, as you can see from here, so we've got volts and metres there. And those, it can be shown that volts per metre is the same thing as newtons per coulomb. So it's not like it's a different quantity, it's the same quantity electric field strength, but it's more convenient because to think of those units because we've got volts and voltage and distance there. Now if we were to double the potential difference between our plates, so instead of got plus V, let's have plus 2V, well now we get twice as many lines per unit area, so we've got more field lines there, and that's consistent with what we saw previously as well. More field lines per unit area means stronger electric field. Okay, now the other thing we can do, if we go back to plus V, but make the distance smaller, so now they're closer, well, the potential difference is the same, but they're now closer, so according to this equation, the electric field strength is, again, twice as strong. So I've represented that fact by drawing more lines there. So that's with your uniform field, those are the two influences on the electric field strength, the potential difference between the plates and the distance. If I had made that 2V as well, then it would be twice as strong as that field, so that would be 4 times the original. Alright, now we have a positive and a negatively charged plate here, and we can use this arrangement to deflect charged particles. So if we fire a charged particle, positively charged through this arrangement, then it's going to be attracted towards the negative, repelled from the positive. And if we fire a negatively charged particle through, then we've got it being deflected upwards. And this trajectory is similar to projectile motion in a uniform gravitational field. Okay, so the difference here is, whereas with the gravitational setup, the deflection is always towards the centre of the Earth, if we were thinking about it in terms of the Earth. Here it depends what charge you have and what the arrangement of the plates is. Okay, so if we consider the positively charged particle here, its horizontal component of the velocity is constant, so it stays at constant horizontal velocity, but it's accelerated towards the negative plate, so there's acceleration in the vertical direction. Onto radial electric fields, and when you have point charges, so very, very tiny charges that are spherical or charged spheres, then they create radial electric fields in the space around them, represented this way. We're just looking at a plane here, so here's my charged surface, charged sphere rather, and these field lines are all going towards the sphere because it's negatively charged, and they're all meeting that surface at 90 degrees, and due to that fact they diverge as we move away from the sphere, or converge as we go towards it. The field strength for radial fields obeys an inverse square law of distance from the centre of the charge. So we're taking the centre of that as our reference point, and the electric field strength here is stronger than here, and the way that it varies is according to this equation here. So you can see it's an inverse square law where r is the distance from the centre of the sphere. So E is equal to 1 over 4 pi epsilon naught being the permittivity of free space. In simple terms, that's how easy it is for the electric field to permeate through a vacuum. So now these are all constant terms here, 4 pi and epsilon naught. Epsilon naught is 8.85 times 10 to the minus 15. So, and that's in your data book as well. So that's all constant, and often we can just use this other constant k, which is equal to 1 over 4 pi epsilon naught. Anyway, so the charge here, take the magnitude of the charge, multiply it by that constant, divide by r squared at the point you're interested in, and that tells you the electric field strength. So that's radial electrical fields. Now what if we take two charged objects, separate by some distance, we want to calculate the electrostatic force of attraction or repulsion? Well, Coulomb discovered the law that tells you the force between these two charges. So if we take two charges, Q1 and Q2, then, and their separation is r, now that's from the centres of Q1 and Q2. So the force is directly proportional to the product of the charges, so we get Q1 multiplied by Q2 and inversely proportional to the square of the distance. So here's our constant again. This is the constant of proportionality here, which is equal to 1 over 4 pi epsilon naught, so it's the same constant we saw previously. Product of the charges Q1, Q2 over r squared. If you have like charges, so if they're both positive, for example, then your force will be positive. A positive force means that it's repulsive, it's forcing them apart. And if you have opposite charges, so a positive and a negative, then you'll get a negative force, and that means that it's attractive. And if you remember, for gravitational forces, the force is always negative there, masses always attract. So that's always negative. Here it can be positive or negative. Similarly to two positive charges, two negative charges gives you a positive force also. And those forces are always going to be the same magnitude, so because you're multiplying out the two charges, it doesn't matter whether this one's bigger than that one or this one's bigger than that one, the product is always going to be the same. So if this is 1.6 times 10 to the minus 19 and this is twice that, 3.2, you'll get one force for this and you get exactly the same force for this. So for a particular situation, forces are always the same, and that means that it's consistent with Newton's third law. So if body A exerts a force on body B, then body B exerts an equal and opposite force on body A. Alright, so those are electric fields and electric forces. Let's look at magnetic fields now. So we have three magnetic materials. There are other materials that are partly magnetic, but these are the three magnetic materials that you need to know. They are iron, nickel and cobalt. So those are your three materials. And any piece of magnetic material always has a north and a south. So if I take a piece of magnetic material, one end is going to be north, one end is going to be south. And then if I were to cut a piece of magnetic material, then if I cut here, then this side, the right side of the left piece will be south, and the left side of the right-hand piece would be a north. It would become a north. And that's because this north-south arrangement is built into the material at the atomic level, so wherever you take a cut, the atoms are always aligned north-south. So it doesn't matter where you take a cut, it's always going to be like that. If you have like poles, so if you take two north poles, bring them close together, they're going to repel. And if you take a north and a south, they're going to attract. So just like with electric charges, like charges repel, opposite charges attract. And we represent magnetic fields also with lines. So here are the magnetic fields for this bar magnet here. And you can see the field lines going around north to south. So that's how we would represent the field lines for that bar magnet like that. That's an important shape which will come up later on as well when we look at solenoids. You can see the field lines generally coming out away from the north there and going around to the south. The magnetic field strength is a quantity called magnetic flux density. That's given the symbol B, and the unit of that is the Tesla, named after Nikola Tesla, and he was from Croatia. If you have a large flux density, so you have a strong magnetic flux density, a strong magnetic field, then that means you have more lines per unit area. So you can see the field is stronger here than here. Alright, so those are magnetic fields for permanently magnetic materials there, like bar magnets and so on. What about conductors? Conductors consist of moving charges, and moving charges in them, and moving charges create magnetic fields in the space around them. If we take a straight wire, that has a circular magnetic field around it, and the field is stronger, closer to the wire, as you might expect, weaker the further you are away from the wire. In order to work out the direction, so the magnetic field is going to go around the direction of the current, okay, so it's circular in that way. You need to use the right hand grip rule, so you take your right hand and you make a grip like this. So you align your thumb with the direction of the current, and my fingers indicate the direction that the magnetic field will go around the wire. So it's going to come out of the board on the top and into the board on the bottom, so the field would look like this. So that's behind it, it's going up and then coming around out on top of the board, on top of the wire, into underneath. That's the right hand grip rule. Let's see how we deal with situations where current is going into and out of the plane of the board. So here, this is my wire, and it's carrying current into the plane of the board. And we denote that with a little cross, or an X. So this X indicates current is into the board. So I take my right hand grip rule now, right hand grip. You can see that my fingers are pointing in the clockwise direction, so the field goes in the clockwise direction. And you can see also that the field lines are getting further apart as we move away from the wire, indicating that the field strength is weakening as we move away from the wire. So that's the current into the plane of the diagram. If it's coming out, we use a dot to indicate the current direction there, and the right hand grip rule gives us the field direction again. So those are my straight wires carrying current into and out the board. You can also use the dots and crosses to indicate magnetic field direction also. So if I now take that straight current carrying conductor, it's now carrying it left to right here, well the field is going into and out of the plane of the board. So on top, just as before, it's coming out of the plane, and because the current is that direction, and on the bottom it's going into. So I've indicated that. I've also indicated the weakening field as you move away from it, because those are getting further apart on the top and further apart on the bottom there. So that's looking at the wire from the side, and I'm using the dots and crosses there to indicate the field direction. So that's straight wires. Now let's look at solenoids. A solenoid is a coil of wire, so we've taken the wire and we've coiled it, and I'm passing current in one side here, it's coming out the other side there. And these solenoids have field patterns like the bar magnet that we saw earlier, so I said that it was going to come up again. So you can see this similar field pattern. The reason for that is that this was a straight wire, but I've coiled it up, and that circular field pattern has combined to form this pattern that's like a permanent magnet. So this is an electromagnet. And now you can work out which way north and south is from the current direction. If we look at the north end, okay, now this current is coming out the back, so it's coming down from behind, okay. Here it's going over at the front, it's going around, so it's going up and then to the front, then the back, and then coiling around, coming out the back there. Okay, so that's the current direction. So if we look here, the direction that the current is flowing at the north end, if we were to look at it from this side, it would be going anti-clockwise. Okay? So the current direction is anti-clockwise around this coil. Now if you draw an N in that circle, and then put arrows on the end of the N, well that indicates that rotation, doesn't it, for the current direction. So that's a very convenient way of remembering it. So if you knew the current direction, you could determine which pole you have. That's right, yeah. North. Okay, so you know it's north. Also, if you knew that it was north, you could work out which way the current direction was by drawing the N in there. Okay, so that's the first thing. Then you could do a similar thing for the south end. Here, if I was to look at the solenoid from this side, the current direction is going clockwise. So I've drawn it clockwise here, and I draw an S in there, put arrows on the end. Lo and behold, the arrows indicate that clockwise rotation, so we can apply a similar principle there. Okay, so that is solenoids. Now let's look at the magnetic forces on conductors. If we were to put a current carrying conductor into a uniform magnetic field here, so I've got a uniform field where I've got the north end of the material pointing towards the south end of the material separated by space, so I've got a uniform field there. Now the field, this green field here from the uniform arrangement is going to interact with the field from the current carrying conductor. The current carrying conductor carrying current into the plane of the board. So we get those two fields. And they will combine to form a field like this. So it's almost like the field of the conductor is pulling those straight field lines up and over in some cases and forcing these ones down. So we've got this space here, and this uneven distribution of field lines here is going to exert force on the conductor, and the force is going to be down here. You can imagine the field lines, they want to spread out here, and there's plenty of room for manoeuvre here. They want to open up, they can accept that conductor moving down, so the conductor will experience a force downwards. I'm not saying that's the reason, but I'm just saying you can imagine those field lines, they want to spread out, and there's plenty of room for them to spread out into here, so they're going to force the conductor down in order to do that. Okay, so the other thing you can think of, you've got a stronger field there, weaker field there, so it's going to force it down. So we've got this force, and you can use a mnemonic from Fleming, who was an engineer who lived 1849 to 1945. He came up with a way of working out that force direction on the current carrying conductor in a magnetic field, and that is Fleming's left-hand rule. So this is a picture that I've tweeted, one of my Twitter summaries for Fleming's left-hand rule. So you take your thumb, index finger, second finger on your left hand. This only works with your left hand. And your thumb, you have to hold them all perpendicular to each other. So the thumb is up, index finger is forward, and the second finger is perpendicular to both, like that. So that's the only way you can do it once you've got those two lined up. The thumb represents the direction of the force that the conductor will experience. This is the magnetic field, which in this case would be left to right because it's north to south. And this is the current direction, which in this case would be into the board. So you can see once I align, because the two things I knew were the field and the current, I know then that the force is down. If I align my fingers with the diagram. It's important that you keep these all perpendicular to each other, exactly like this, and you've got to move your whole hand in order to align the quantities with the situation that you're facing. So don't start, people do this kind of thing. You know, you can't start adjusting the direction of current with respect to the field or anything else, okay? So you can't start doing anything else. You have to keep these all perpendicular to each other. Okay, so that's how you use Fleming's left-hand rule to determine the force direction. So that tells us the direction, Fleming's left-hand rule for the direction of the force. If we take our current carrying conductor here, this case here, it's in this orientation, which is at theta to the magnetic field. So the magnetic field is left to right here. Now only the part of the wire that is actually inside the field is going to experience a force. So this bit of wire here outside the field, that's not going to experience a force, nor is this bit down here. So it's just this length here. So the length of the conductor in the field is important, so that's L. Only the component of the current that's perpendicular to the field is also going to count. So doesn't matter that there's all this current flowing through here, some of it is not perpendicular to the field. The perpendicular component is I times sine theta, where theta is as I've shown here. So now the product of flux density, that perpendicular component of the current and the length will tell us the field strength. So, sorry, not the field strength, the force. Force is BIL sine theta. So that will tell you the magnitude of the force for a general situation where the wire is at angle theta to the field. Now, you can now see if the angle is 90 degrees, so if this was actually vertical in this diagram, then the force would be equal to BIL. Okay? And if theta was 0, then sine of 0 is 0, and therefore the force would be 0. So if I have the current carrying conductor parallel to the field lines, then it won't experience a force. So that's how you work out the force, and you then can use this equation and Fleming's left-hand rule to determine the direction and the strength of it. Where you've got an angle here, you're going to have to use this perpendicular component of the current in order to work out the direction. Okay, so it should be into the plane of the diagram there. Alright, so you can see I'm moving my whole hand and wrist to make sure I'm using Fleming's left-hand rule correctly. Okay, this is actually the equation that defines magnetic flux density. You rearrange it for B. B is equal to F divided by IL, and so that tells us the amount of force exerted per unit length of conductor carrying per unit current perpendicular to the direction of the magnetic field. So it tells you, I think that grammar is a bit off actually, but so if you have current carrying conductor, so you've got your carrying a unit current which is perpendicular to the direction of the field. So if you want to define it, you want to set theta to 90 degrees so that it's perpendicular. And the unit there, you can use that to then define the Tesla. 1 Tesla is equal to 1 Newton per amp per meter. Okay, so that's our flux density. This magnetic force is used in electric motors. What you do, you take a rectangular coil like this, place it in a magnetic field. This dotted line indicates the axis of rotation of that coil, so that coil can be rotated around there. We'll pass direct current through that coil, and at this moment in time the coil is horizontal. Now we'll apply Fleming's left-hand rule to that situation. So the current is coming in here. Okay, so the current direction, we've got the field there, so the field is left to right, so the force is down on the left. So that current goes around here and down this way. So the current is now out, the field is to the right still, so the force is up. Because the current switched direction on this side of the coil, experiences a force upwards. Now we have these two forces, they're equal in magnitude because the current in the coil is the same, the field strength is the same, and that is going to set up a couple where we have two equal and opposite forces. So one's up, one's down. That will cause the coil to rotate. So we've got a couple set up. The energy conversion that takes place is we have the conversion of electrical energy to mechanical energy because you've got that rotation. So what we do is we fix the axle of the coil onto the axle of a little car, for example, or a big car, and that will force the axle to rotate. Slip rings would be used here so that the coil could rotate without twisting up the wires, and it will keep whenever the coil is horizontal, it will keep the current flowing in this direction so that the forces when the coil is horizontal are in the same direction. When the coil is vertical, the slip rings will cause the coil to become disconnected for that moment, and the momentum of the coil will carry it through so that it becomes near horizontal again, and then you get the couple set up again so it keeps rotating. And loudspeakers also use this effect, but they have different energy conversion. This converts electrical to sound. Instead of having this coil rotating in the field, what they have is they have a magnetic field in a circular arrangement, and then they have a coil there, and you pass an alternating current through the coil. So that means that the coil will want to oscillate because sometimes it experiences a force this way, sometimes this way, so it'll oscillate in backwards and forwards. Okay. Right, so we've been looking at conductors which are carrying a current through a magnetic field, but if you have isolated charges as well moving through a magnetic field, they will experience a force too, and the force they experience is given by BQV. B, flux density, Q is the charge on the particle, and V is the speed at which they're moving through the magnetic field. So we use Fleming's left-hand rule again, but the thing you have to watch out for here is the fact that because we had a negative charge, the conventional current direction, which is what the second finger indicates, is in the opposite direction to its motion. So at the top, the negative charge is moving left to right, so the current direction would be to left field is into the board, indicated by the crosses, so experience the force down here. Now, it will then change direction because it's being accelerated by this force, in this case down. So then its velocity vector is going to change direction. That means that the conventional current direction changed, and therefore the force has changed direction. The force always changes as the velocity vector changes, so that it is always perpendicular to the velocity. So when you have charged particles moving through a magnetic field, you have circular motion. So when we were looking at charged particles in a uniform electric field, that was motion, it was like projectile motion. But here it's circular motion for a uniform magnetic field. So, let's look at some other quantities we can work out with our equations that we know, including the one we've just seen for the magnetic force. We're going to accelerate our charged particle with an electric field. That's what this is indicating here. We've got a negative plate, we've got a positive plate. So we're going to accelerate it through that electric field, and then it's going to enter our magnetic field here, and there it will experience the magnetic force, which is perpendicular to the velocity. So here the force is going to be in the same direction as the velocity. To accelerate it, speeds up, comes out here, goes into the magnetic field there. Okay. Once it's there, it's got certain velocity, which we can determine from the electric field. So, the magnetic force here is going to provide a centripetal force because it's circular motion, F equals BQV. And because it's a centripetal force, that's equal to mv squared over r. We can rearrange that for v, cancel out some terms. So we're looking at these two parts of the equation. BQV is equal to mv squared over r. You can see this v will cancel out one of these v's here. So then we get the velocity in terms of b, q, r, and m. The electric field strength we used here to accelerate it, that increased the kinetic energy. The kinetic energy is given by the charge multiplied by the potential difference we used to accelerate it, so VQ equals a half mv squared. So now we've got another expression for the velocity, which is root 2vq over m. Don't confuse the capital V here with the lowercase v here, so that's the potential difference, and that is the velocity. So let's combine those two equations for the velocity. So bq r over m is equal to that side. Combine them over there. Let's rearrange that. So now we've grouped some terms together and rearrange again. Now we've got the radius that particle will undergo in its circular motion in terms of the voltage that we use to accelerate it, the mass of the charged particle, the magnetic field strength, and the charge of the particle. So now we have a way of calculating it that's in terms of properties that are easy to know for a given charged particle in a particular situation. And then you know how, if you change this accelerating potential, how the radius will change, and if you change the field strength, how that will change things as well. So how you change the radius. This is r squared, so you might want to square root both sides so that you've got r on the left. Right, is that all very useful? Yes, if you use it in velocity selectors. So let's look at another application of this electric field and magnetic field, however in a slightly different way. And we'll see how velocity selectors are relevant to mass spectrometers as well, where you might care about your accelerating potential and then the radius of a circular path followed by charged particles. Right, so we can use electric fields and or magnetic fields to deflect charged particles. We can use electric fields here. This is the force that the charge would experience. This is due to the electric field, and this is the force that a charged particle would experience due to the magnetic field. we can actually use both of those fields at the same time to apply equal and opposite forces to particles that meet certain criteria. So, here's my electric field here, and the uniform magnetic field is going into the plane of the board. So we've actually got both at the same time. If we are able to exert the same forces, electric and magnetic, on a charged particle, then we know that EQ is equal to BQV. And so what this will do is any particle moving at this velocity, which is equal to E divided by B, because the Q is divided out here, those particles will experience the same force. So they will go through this arrangement undeflected, but any particles not at that velocity, any charged particles not at that velocity, will be deflected by that arrangement. So we can use that to select charged particles that have exactly that velocity. So there's my negatively charged particle. It experiences an electric force to the left because it's negative, attracted towards the positive plate, and the magnetic force is to the right. So conventional current is down, field is into the plane of the board, so the magnetic force is to the right. So that particle was going at the velocity equal to the electric field strength divided by the magnetic field strength. So that was undeflected. But if the velocity were slower, so let's take another particle which is going to have a slower velocity than E over B, that will mean that the magnetic force is smaller than the electric force, and so it will be deflected to the left. So this one is not successfully passing through my velocity selector, because after going through my velocity selector, it's then going to go on to do something which only the ones going straight down the middle are going to go into. The others are not going to make it there. And if the velocity is larger than that, then it will be deflected in the opposite direction because the magnetic force is bigger. If you can't immediately see that, then you can always just think about the fact only the magnetic force depends on the velocity. So therefore, if it's going faster here, you can see the magnetic force will be bigger. So you can just look at that equation to understand which way it will be deflected. The mass spectrometer, as I said, is an application of the velocity selector. So here is the velocity selector in this particular arrangement. We've got the accelerating electric field here to accelerate our charged particles from our source here into the velocity selector, and then we have a uniform magnetic field here. In this region here, it's only the magnetic field here, and once the charged particles enter the magnetic field, they undergo circular motion. So, in our velocity selector, we will only get charged particles with charge Q coming out of the velocity selector correctly, so coming out of here at the right speed. And then the magnetic force provides a centripetal force, so FB, we've already seen this arrangement here, BQV equals mv squared over r. If we rearrange and substitute for V, where V was E divided by B, then substitute that in, and we get BQR over M is equal to E divided by B. If we make R the subject, then R is going to be equal to E over B squared multiplied by M over Q. So what that means is that each ion's deflection in the magnetic field is going to depend only on its mass to charge ratio. Okay? So you can detect for certain mass to charge ratios at certain radii. So you adjust the position of your detector to specific radii, and you can detect whether particles with the corresponding mass to charge ratio are in your sample. Okay? So the radius depends only on the mass-charge ratio. So that's the use of the velocity selector, but also we've used that accelerating potential here and the uniform magnetic field providing a centripetal force. Okay, now we're on to looking at some magnetic quantities before we start to look at induction. First quantity, I just need to go back because, right. Magnetic flux density, which is B, that's the number of field lines, or flux, amount of flux, passing perpendicularly per unit area. So we've already come across that. It's B, it's of no specific area, it's just a general area. Magnetic flux, so this is not flux density, but magnetic flux, which we give the Greek symbol phi. That's the number of magnetic field lines passing perpendicularly through through a specific area A. So I've defined my particular area A here, and that plane is at an angle theta to B. So if theta was 90, then the flux would be B times A. It's the magnetic flux density multiplied by the area that you have. But in this case, because it's at some general angle theta, phi would be B sine theta multiplied by A. So that's how you'd work it out for that particular case. And the unit of flux is the Weber, named after Weber, who was a German physicist working in the 1800s. The symbol is capital W lowercase b. 1 Weber is equal to 1 Tesla meter squared. So that's flux, and then we have flux linkage. This is where you have a coil that's got n number of turns in your magnetic field. So flux linkage is n phi, that's the number of turns multiplied by the flux. So this is the total flux linking n turns of wire through area A. So what I did here is I just multiplied the number of the area by n turns there. Okay, so and the unit for flux linkage is also Weber because n is just a number, dimensionless quantity, so it's just multiplying it by a number there. Alright, now we can start to look at some induction. And what we're going to do firstly is consider a straight wire that is cutting through uniform magnetic field lines. So we're moving our wire, which doesn't have any current flowing through it ordinarily, through that magnetic field. Now within that wire you have charged particles. I'm sure you appreciate the fact that any metal wire has lots of electrons in it, and some of those electrons are free to move. So as we move our wire through the field, we now have moving charges in a magnetic field. So they're going to experience a force. So we're moving our wire through there, and if we look at it from a magnified point of view, so here's our field, and within the wire we have some charges. We've got a negative charge here moving down, so the conventional current is up, and the field is to the right, so the force is into the plane of the board. So if you imagine this end of the wire is going into the board, right? So that electron here, negatively charged electron, is experiencing a force. What are we doing? Yeah, sorry, because the velocity is down, current is up, so it's experiencing a force into the plane of the diagram, which happens to be along the direction of the wire, if you imagine the wire is going into the plane. So, and that's always the case. Whenever you move your conductors perpendicular to the field, the charges in it will experience a force that is parallel to the wire. And that means that we're going to get a flow of charge along the wire, or electrons are all going to be forced up this end of the wire, leaving positive charges behind, so that will set up a potential difference. We've got an induced EMF in the wire. And if we were to connect this connect this wire to a circuit as we moved it through the field, like an ammeter would be a good example of a circuit we could connect it to, we would see that current would flow. So just doing it by itself, yes, okay, charge is flowing up one end of it, but it's not going in a loop. So we've got a potential difference set up, but as we connect it to a circuit, then we get current flowing around. So we've applied Fleming's left-hand rule to work out the direction of this force. And when we've connected it to a circuit, we get current flowing, which is going to be opposite direction to these negative charges, all right? So if the force on the negative charge is that way, so they're being accelerated that way, then the current, conventional current, is in the opposite direction. And here we can use Fleming's right-hand rule to work out the direction of current flow for induction. So we've got the motion of the wire is down. So we take Fleming's right-hand rule. The thumb on my right hand indicates the motion. The index finger is the field direction, so that's to the right. And then the direction that my second finger points will give us the current, which in this case is out of the plane of the diagram. Okay? So the same things applies for Fleming's left-hand rule. You've got to have your thumb and two fingers all perpendicular to each other and move your hand around. Index fingers always point forwards, thumbs up, and second fingers are perpendicular to those. So this is Fleming's right-hand rule. Don't confuse it with Fleming's left-hand rule. This is for force or current carrying conductors. This is for electromagnetic induction. So that's how we can work out the current direction for a straight wire. And now we're going to look at Faraday's Law, which is after a British physicist called Faraday. And this is concerning coils. So we've been looking at straight wires, this is for coils. You can get EMFs induced in a coil if you change the flux linkage in them. And Faraday was conducting an experiment using coils and trying to work out how to work out the induced EMF, and he realised that what you need is a change in the flux linkage, not just a large flux linkage in a coil. You actually need to have a change in it. So he discovered that the induced EMF is directly proportional to the rate of change of flux linkage. So its rate of change, the faster given flux linkage is changing, the larger the induced EMF. So Faraday's law, the induced EMF is proportional. This is the rate of change of flux linkage here. Now if we take a magnet and coil, in order to induce current in the coil, or to induce, if it's not connected to a circuit, to induce an EMF in it, then I need relative motion between the magnet and coil, and that's essentially what Faraday's law is telling me. So I can move the move the magnet through the coil, and that will induce an EMF, and if it's connected to a circuit, it'll allow a current to flow in the coil. Now you may not have noticed, but as the magnet was moving into the coil towards the midpoint, the current was flowing in one direction, and as it moved out, the current flipped direction. Okay, so the direction of the current is important. At this stage, we don't know what that relationship is, but you can already appreciate from the straight wire situations that the current direction depends on the direction of the relative motion. Okay, just like with the straight wire, so you can appreciate that fact. Now let's look at Lenz's law to see how that plays out. The induced current, because you're moving a conductor through the magnetic field, you've got a current flowing, and now because this is all taking place in a magnetic field, that means you have current flowing in a magnetic field. What do we know about current flowing in a magnetic field? We know that it experiences a magnetic force. So let's investigate this with Fleming's right-hand rule and Fleming's left-hand rule. Okay, so this is another picture that I sent out on Twitter demonstrating this point. So we're inducing current and we apply Fleming's right-hand rule. It doesn't really matter which orientation it is for now, for this point. But if I say we're inducing a current which is flowing in this direction, let's look at the direction of the magnetic force on that current carrying conductor. I'm just considering a straight wire here. So I align the current with the induced current direction, and now I align the field directions because it's the same magnetic field for both of these circumstances. And you can see that the magnetic force on my left hand here is in the opposite direction to the motion. So it's in the opposite direction to the motion. So if we use these two rules that we've already seen, we can now better understand Lenz's law. Lenz discovered, and he was born in Russia and lived a long time in Germany too, another German physicist here. He discovered that the direction of the induced EMF is such that the current that is induced is going to flow so that it opposes the motion or opposes the change which caused it. So now, let's take Faraday's law, and we can now say equals if we introduce this negative. So the induced EMF is equal to the negative rate of change of flux linkage. That's why there is a negative in the equation, because the induced EMF has got to oppose the change that caused it. If we think about it in terms of energy as well, this will make more sense. Lenz's law arises because of the conservation of energy. If we look at the energy transfer that's actually taking place, because we're moving a magnet relative to a coil, the magnet has kinetic energy, so we've got a kinetic to electrical energy conversion. So let's give some values to this. Let's say the initial kinetic energy of the magnet is 100 joules, and the electrical output we get from this is 40 joules. If we didn't have Lenz's law, there would be no kinetic energy loss. Okay? So we've got kinetic energy being converted to electrical plus kinetic energy, because the magnet is still moving, so it's still got kinetic energy. Alright, so let's put the numbers in then. We started off with 100 joules of kinetic energy. We get 40 joules output of electrical, but we've still got 100 joules of kinetic energy because there was no loss in the magnet's kinetic energy. So we've just created energy. We've just created 40 joules of free energy, but you can't do that, as we know from the conservation of energy. So it's impossible. With Lenz's law, what happens is you have this conversion taking place, Ke to electrical plus Ke, but now we've got 100 joules being converted into 40 joules of electrical, but the kinetic energy of the magnet is reduced, leaving us with 60 joules. So now we've got numbers that add up. Energy is conserved, we didn't create anything, so good times, we're consistent with what we know to be true in physics. So Lenz's law explains it, well, that is due to the conservation of energy. If you want to maintain that 100 joules of kinetic energy for the magnet, if you want to keep it moving at a constant speed, then you're going to need to input more energy. So you need to find that from somewhere like chemical energy would be a good example. So you keep putting more chemical energy in and you can maintain your Ke. Alright, now Lenz said that the induced current has got to flow so that it opposes the change that produced it. So let's look at some actual practical outworkings of this. The straight wire moving through a uniform magnetic field we've already looked at, and that's straightforward anyway, using Fleming's left-hand rule, Fleming's right-hand rule, okay? So that one's straightforward. What about a magnet moving toward a coil? Here's my magnet. South pole is towards the coil, okay? the current is going to flow in that coil so that it repels the magnet. Okay? So we move the magnet towards it, that's going to induce a south pole on this side so that it repels. By repelling the magnet, slowing it down, it's opposing the change that produced it. Okay? And because there's a south pole here, we know there's a north pole on the other side. So that's the first situation. And then the reverse of that, if the magnet now moves away from the coil, current will flow so that it attracts the magnet. So let's move it away, and we get a north pole set up here so that it attracts this magnet and therefore opposes that motion. So if you move it towards and away from the coil and you're looking at the voltage output you get from the coil, you'll see that it will keep reversing direction. Another good example actually is to drop a magnet through the coil and look at the voltage output you get. So what we're going to get here is going to get repulsion and then attraction. So it's moving towards the coil as we drop it above, and then it will drop out the bottom and move away from it. So it then needs to attract the magnet upwards to oppose the change that caused it. Okay? But you're only going to get a voltage output from the coil whilst the magnet is close to it and then it's actually noticeably in the field. Okay, let's look at the induced EMF output for the magnet drop. We get these two peaks, and so as the magnet moves towards the coil at velocity v1, but it's accelerating obviously, we're going to get the first peak induced of the EMF. Now the peak is broad, so it's wide here, because the magnet is moving slower here, so it's close to the coil and influencing the coil for longer than it is when it's at the bottom and moving much faster. Okay, so V1 is less than V2, like the average speed up here is slower than the average speed down there. It's also lower than the magnitude of this peak is less than the magnitude of this peak here. Because it's going slower, the rate of change of flux linkage is smaller. Okay, this is where the magnet is at the midpoint, and we see that it reverses direction because when it's above, the north pole is facing towards the coil, it needs a south pole at the top, sorry, a north pole here to repel it. Okay, when it's at the bottom, the south pole is facing towards the bottom of the coil, so we need the north over here now to attract the magnet. So the north pole had to switch from there to there. In order to do that, current direction would have to reverse, or the induced EMF would have to reverse. Okay, and this peak is narrower because it's moving faster, so it's close to the coil for a short period of time. Okay, and the induced EMF is high because the rate of change of flux linkage is larger. All right, that's some examples of applying Lenzs Law to help us and Faraday's Law, in fact, to understand what's going on with magnets and coils. Let's look at the AC alternator, which is a way of generating electricity. Alternators generate alternating current. Okay, so what we do is take our rectangular coil, much like the one we had for the motor effect, in fact, we put it in a magnetic field, and then instead of passing a current through the coil to make it spin around, we actually spin it around by other methods, and we induce an EMF and then induce a current in our circuit in the coil. Okay, so here you might use a turbine, like most power stations use a turbine to drive an alternator to generate electricity. As the coil rotates, the flux linkage is going to change. As you can see, when the coil is vertical, you've got loads of flux lines going through the coil perpendicularly. And when it's horizontal, you've got no flux lines perpendicular to the coil, so you know the flux linkage is changing as you rotate it. We need to consider the orientation of the coil though. We need to consider the component of flux that is perpendicular to the plane of the coil. So if we take from perpendicular to the plane of the coil, the angle between that and the flux lines, that angle is theta, so that's our orientation. The component of flux that is perpendicular is phi cos theta. Okay, so now our general expression for flux linkage is going to be n multiplied by the perpendicular component of flux, so that's n phi cos theta. When the coil is vertical, theta will be 0. So if we rotate that so it's vertical, those two lines are parallel, the field line and the dotted line here. So theta is 0, flux linkage will be equal to n phi, that's our maximum flux linkage. When the coil is horizontal, theta will be 90 with the flux lines, so the flux linkage will be 0. Okay, so 0 theta, cos of 0 is 1, cos of 90 is 0, giving us 0 flux linkage. Okay, so that's how flux linkage changes during the rotation. As we make a complete rotation, so if we go from 0 to 180, the coil is going to reverse direction, and that is the reason that we get an alternating current generated, because the direction of the flux is going to reverse in the coil, and therefore we've got the rate of change of flux linkage changing. So changing sign, and therefore we get the induced EMF reversing direction. Okay, so as we rotate it, the flux changes direction in the coil, meaning that we have a reversal in the induced EMF direction. Right, let's plot this then. Okay, the first graph we're going to look at is flux linkage with time. The flux that links the coil will vary with angle theta according to the cosine relationship, but because theta changes directly with time, the function with time is also a cosine relationship. So because theta is changing directly with time, that's why it's a cosine relationship still. Okay? Right, let's start off by plotting some values. Yeah. Our maximum flux linkage is n phi. The minimum magnitude is 0. Then we're going to get a maximum when the coil is vertical again, but reverse direction. So that then the flux linkage will be minus n phi. Okay. So that's the first thing to note. Now we're going to mark out the key times with respect to the cycle of the coil as it rotates. So starting off with 0, this is quarter of a cycle, half a cycle, 3/4. That's a full cycle, full time period to complete one revolution. Then 5/4 and 3/2. These are the corresponding angles of the coil for the first cycle. So it starts off at 0, then it goes to 90, 180, so on. Let's plot some data points at those times. So we start off with m phi, because when theta is 0, we've got that maximum flux linkage. When the angle is 90, the coil is horizontal, so we get 0 flux linkage. The coil is vertical again here, but that's where it's reversed. Then to 0 and back up to the maximum again, maximum positive. And we know it's a cosine function, so now we can draw a nice cosine curve between those points. So we get that. Now that's flux linkage with time, that's not our output yet, so that's the first graph. So, and don't forget, if you ever had to draw these graphs, you get marked on the shape of the sinusoidal curve, so make sure you draw them nicely. Right, let's fade that one out, and we'll look at the rate of change of flux linkage graph. If you have rate of change of, that means we're going to plot the gradient. We're looking at the differential of the previous graph. So that's why I've left it here, so we can look at the differential of it. We're plotting the gradient. If you differentiate a cosine function, you get a negative sine function. So we know it's a negative sign. That's useful to know. But if we look at the gradient, then here, the gradient is 0. Here it is maximum and negative. Here it is 0. Here is maximum and positive. Here it is 0, maximum and negative, and here is 0. So we can actually plot some points. So when the coil is vertical, you get 0 rate of change of flux linkage. When it's horizontal, you get maximum rate of change of flux linkage. This is maximum and negative though, because you've got that negative gradient. Back to 0, back to positive. Okay. The other thing you can think about here is if you think of this is a rectangular coil rotating in a magnetic field, the top and bottom edges of the coil are what are cutting through field lines, right? So when the coil is vertical, the field lines are horizontal, and that top part of the coil is also moving horizontal, so it's moving parallel to the field lines there. 0 rate of change of flux linkage. It's not cutting any field lines there. When the coil is horizontal, however, the top of the coil is moving down, so it's cutting through those field lines. So we get it, and it's cutting right across those field lines. So here it's going to be that maximum, and here, because that's where the coil is horizontal. Okay. Anyway, now let's plot our negative sign, and we get this graph here. Okay, so that's our negative sign. So whichever method helps you think about the problem and solve the problem best, just stick with that. Right, let's crack on. And now we're looking at, that's what I just said about moving parallel to the field lines, moving perpendicular to field lines. Right, the induced EMF graph is this. The induced EMF is equal to the negative rate of change of flux linkage, so therefore it's a positive sine function. There's my positive sine function there. So it's just flipped it in the x-axis. Okay? Coil is vertical, horizontal, vertical. Alright, so those are 3 graphs for the AC alternator. Last thing we need to look at now is transformers. Transformers use electromagnetic induction to increase or decrease the voltage. There are 3 components to them. They have a primary coil, secondary coil, and an iron core. Okay, so you've got a primary coil and a secondary coil, and the number of turns on these 2 coils is different. Transformers only work with AC. You can't get these working with DC. We need to have a change of flux linkage in the secondary coil, which means we need to have a change of flux through this primary coil here. Okay. The purpose of the iron core is that it maximises the flux through both coils. So I've drawn on some flux lines now, and that's what they would look like. They're going all the way around that iron core nicely. So we're getting, hopefully, as much of the flux is produced by passing a current through the primary coil will go through the secondary coil. Now when we put an AC in here, or if we were to just pass direct current through here, we would get a magnetic field produced in the solenoid, just as we've seen before. And then that flux is going to go in a particular direction through the secondary coil. But now let's make that an AC. So we've got alternating current. The current keeps switching direction. That means the flux is going to keep changing direction. And that means we've got a change in flux linkage happening in the secondary coil. That is what induces an EMF here. So that gives us a voltage output. All right, and as I said, the number of turns in the primary, NP, is different to the number of turns in the secondary coil. And because of that, that's going to give us a different voltage. So the EMF here is going to be equal to the rate of change of flux linkage. Now, the flux through the coils is the same, but because the number of turns is different, the flux linkage will be different here to here. That means that this voltage will be different to this voltage. Let's look at the two types of transformer you can have so that becomes clear. If you have a step-down transformer, then we've got the same flux through the coils, but because NP is bigger than NS, and that's what makes it a step-down transformer, the fact that the number of turns here is bigger than there, then that will give us a larger flux linkage in the primary than the secondary, so the induced voltage in the secondary will be lower than the primary voltage. So we're stepping down the voltage is reduced. Let's look at the relevant equations here. Vp is rate of change of flux linkage for the primary, Vs is rate of change of flux linkage for the secondary. So if we divide these, the only term that is different, because phi is the same and delta t is the same, is Np and Ns. So Vp over Vs is equal to Np over Ns. That's the equation that you need to know for working out what the voltage output of your transformers is. That applies to step up and step down transformers. Okay, so if Np is bigger than Ns, then Vp will be bigger than Vs. So that's how we know what the voltage output would be. If you wanted to actually calculate voltage in a secondary, then rearrange this equation so Vs is on top, make it the subject of the equation. You can work out this ratio from knowing what the turns are, and then you multiply that by the voltage in the primary to get your secondary voltage. The power input is equal to the power output, okay? So even though the voltage is reduced, we're not losing energy along the way in terms of the actual function of the transformers. So the power input is equal to the power output. Now obviously there's efficiency considerations which I'll factor in a moment, but I'm saying that we're not violating the conservation of energy here by stepping down the voltage. So if the power is equal, then power is IV, so IV for the primary is equal to IV for the secondary. So therefore, if we reduce the voltage, then the current will be correspondingly larger. But as I said, there are efficiency considerations, so the power in the secondary, the power output, is equal to the input power multiplied by the efficiency. So if you had an efficiency of 90%, then the secondary power is equal to 0.9 times the primary power. I've used 90%, that's pretty realistic for a transformer. They're not 100% efficient, but they are very efficient components. They're probably the most efficient component in a power station, for example. So there I assumed that the power was 100% efficient, just so you can see what happens to the current. Right. So the current increase, yeah. And the power losses here would be heat predominantly, so heat in the coils. The coil, when you pass currents through coils, they're a bit hot, so that'd be the main. The reverse of the step down transformer is the step up transformer. So again, flux through the coils is the same, but the number of primary turns is less than the secondary turns, so flux linkage is less in the secondary, and you can see that the reverse would be true for step-up transformers. And that's electromagnetism, and I'm going to stop there and come back and do capacitors for another video.